Welcome back once again. Here we go. Now that we've talked about memory reclamation techniques, let's take a look at when each of these different techniques actually takes place on the system. There's an actual set of formulas that are calculated by the VM kernel to determine what stage in memory shortage is the system in right now, to determine then when or what type of memory reclamation technique should be performed. So how is this done? Well, there used to be, in older versions of vSphere, a straight fixed value called min-free. It was simple. It was it found 6% of whatever you configured as memory on the ESXi host. So say you had 100 gigs of memory, 6% of that would be the threshold of when the different reclamation techniques would kick in. It would start with ballooning when it was at 6%, and then it basically cut that into basically thirds. So when it was down to 4%, then it would start the compression, and then it was down to 2%, it would start swapping. But it doesn't do that anymore, because it turns out you can now add to an ESX server 12 terabytes of memory. So having 6% of 12 terabytes is actually quite a good amount of memory on a system. So now what the system does, it actually does a sliding scale, creating a more appropriate value for staying above in terms of how much free memory should the system stay above. So it's no longer actually called min-free. It's still referred to min-free from time to time, just because that's an easy way to say, okay, our goal is to be above min-free to make the system no longer have to do any kind of serious reclamation. But it's actually now called mem.memminfree% is the actual name. And so what we do here is the system starts doing these calculations. For instance, it'll look to see how much memory is on board the server and then kind of break it down in multiples of, or in powers of 2, basically. So, but it starts with 4. So as you'll note here, for the first 4 gigabytes installed on an ESXi host, right? So that gigabytes 0 through 4 will take 6% of that. If you happen to have 128 gigabytes of memory on that ESX server, that would be 246 megabytes. So 6% of 128 is 246. Then for the next 8 gigs, that would be gigabytes 4 through 12, the system will now take 4% of that and then find 4% of 128, that's 328. Then the system takes the next 16 gigs, so that's gigs 12 through 28. We'll find 2% of that, which of course is also 328 megabytes. So as you can probably gather, most ESX servers that have more than 28 gigabytes of memory, these results are always going to be the same, right? I mean, if you have at least 28 gigs of memory, we'll always do these same 3 calculations. That's always kind of a constant. But then every amount of memory beyond 28 gigabytes of memory. So in our case, we have 128 gigs of memory on memory. So we basically have 100 gigabytes left that the system's going to now look at and say, we're going to take 1% of that, so 1024 megs, and that will be part of the calculation. So then we basically sum up all of these numbers, and this summation is now what the system is going to try to be above at any time, right? That's the goal the system needs to be at, above 1926 megabytes. So now we have that. We can then say, okay, we can gather where we need to be. Then there's also, well, what are the different stages that the system's going to then choose which reclamation technique to perform? So there's, on a vSphere 6 and later system, there are 5 stages of memory or memory states that the system could be in, and that will determine which of the reclamation techniques the system will perform. So for instance, if the server is in its high memory state, we're not doing any serious memory reclamation. The system is actually healthy here, right? It has high amounts of free memory. In fact, what it does, we talked about the fact that there are large memory pages handled by the MMU, right? We take the 4K byte pages and they get allocated into these 2 megabyte size pages. Well, their 4K byte boundaries are still remembered though. They're still saved. So what the system does, it'll actually find those large pages, scan them, and learn about whether or not they have, the 4K candidates out there. But we're not going to take any real aggressive action because remember, page sharing is already disabled. So all it's doing is looking at intra-VM page sharing opportunities. If you've actually enabled page sharing across VMs in some fashion. Again, it's just going to take those large pages and scan them, and any small candidates for page sharing are going to be identified. But if the system starts running low on memory, it may transition into what's called the clear memory state. Now, clear isn't really considered low memory at this point. It's a early warning, early warning. And notice all it does is it breaks those large pages, those 2 megabyte pages, and it's going to actively call page sharing to collapse them into those shareable locations. Now, again, it's only doing this on intra VM levels, but if you enabled inter VM, it would also do that too. So basically, large pages get broken up into the 4K byte pages. As soon as they've done that, then page sharing can start looking for page sharing opportunities for any pages that are allowed to be shared. And that is to basically, the goal of this is to bring the system back to high. But if that's not enough, then the system may transition into what's called the soft memory state. Soft is now when we're going to start ballooning. The goal of ballooning is to bring it back up to at least clear or high. But if it's not sufficient, it may transition into hard, where now compression and swapping will begin. And then that is, again, supposed to take us to high if we do it properly. But if it's still not sufficient and the system transitions into low, well, now the system is at its most aggressive state, right? We are compressing, but we're really focusing on swapping. And the system has transitioned into block, right? Blocking indicating that we are now waiting on the paging activity to finish before doing anything else, right? We're blocking the execution of VMs on CPU. So if you remember when we were looking at the CPU screen, there was that one column called swap wait. Well, that's what's happening here, right? We are so invested in swapping now that we're not going to even let VMs get scheduled onto CPUs. You can't even power on a VM at this point. We're blocking the allocation of a page. This is basically what this is doing here. So no new pages can be allocated. We are busy clearing them through some kind of, reclamation, whether it's through swapping or compression. But you've got more and more aggressive reclamations based on what state the system's in. So putting all this together, we've got our min-free percent value, plus we have our different stages. When do they kick in? Well, what's interesting is the different stages, they kick in when, well, I should say they kick in at different points depending on whether the memory is running short or if the amount of free memory is actually being increased. So are we heading in for more paging? Is the amount of free memory dropping so significantly now we're under pressure? Or are we past that point and now the pressure is basically being lifted and the amount of free memory is actually increasing? So there's basically just different thresholds is what we're getting at here. So notice here, this is transitioning from one memory state to another. When memory pressure is increasing, that is when free memory is decreasing, right? So we're increasing the pressure. We're needing to take far more aggressive corrective action. When the system is at the high state, that basically means, of course, the host is doing really nothing of any significance when it comes to reclamation. But remember, there's this value of min-free, right? This value that the system has calculated. And if we are at 3,000, if we are 3 times that value, right? Whatever the min-free was, we're 3 times that value. So we're 300% of it. Well then, and I wrote min-free here, but that's just because this is easier to write than it is to write min-free percent, right? But whatever the min-free calculation is, 3 times that value is when the system starts to transition into clear. So basically, we were at high. The amount of free memory has dropped. We are now below 300% of min-free. We're in this clear stage, and that's when we're going to start to do what the clear state actions were, which remember, that's breaking up the large pages into 4K byte pages to get more aggressive for page sharing, specifically with intra-VM page sharing. And the goal of that is to bring the system back to high. But if the more aggressive breaking pages up and looking for page sharing opportunities is not sufficient, and the system starts having more memory, being dropped again, now we're dropping below 64% of min-free. So now we're actually less than min-free. So min-free is, this threshold here, right? We are 3 times the value which when we transition into from high to clear. And then if we drop below 64% of min-free, basically we're running just about 2/3 of the value of min-free. And that's when soft transitions and we start ballooning. And we'll balloon and balloon and balloon until we are above the clear value again. But if the ballooning is not sufficient, when we're at basically 1/3 the value of min-free, right, 32% roughly, 2/3, is when we start to transition into the hard state. And that's when we start compression and start swapping. And of course, the goal is to bring us back up above min-free. If, though, the compression and swapping is not sufficient, now we've transitioned into low, which is basically whatever 16% of min-free is, basically a sixth of min-free. Now the system has moved into a blocking state. No new pages can be allocated. So these are the percentages that we transition to when we're basically dropping free memory lower and lower and lower. Once the memory shortage has subsided, now we'll hopefully be able to increase the amount of free memory. The percentages are different. If we are at the low state, we are blocking the allocation of memory pages, and now that has caused the amount of free memory to increase. Well, 24% of min-free is when we transition into into hard. And so you notice these numbers are actually higher. So we're a little bit more cautious here in coming back. 48% of min-free is when we transition to soft. We'll transition from swapping over to ballooning. And then when we cross over the min-free barrier is basically when ballooning stops, and we'll go back to being more aggressive with page sharing. And then when we're 400% the value min-free is when the system is high, and it will be far more relaxed. It won't need to do any kind of page sharing, at least having to forcibly break up pages for page sharing opportunities. So it's interesting to see that these are completely different ranges and thresholds when the memory pressure increases versus when the memory pressure is decreasing. You can see all this, of course, using ESXtop, what state the memory your ESX server is in. So we took a look at the memory virtualized environment, how memory reclamation works with a variety of different reclamation techniques, and how overcommitment affects performance. Basically, it's the paging, the disk I/O, which is going to cause performance issues. If a VM needs access to its memory and it's on disk, we have to wait for the disk I/O as opposed to having to wait to get the data off of memory, which is a big performance degradation to start off with. So in any case, we finished this lesson. We'll take another quick break. We'll come back and we're going to show you the important metrics to monitor when it comes to memory management using ESXtop. So we'll see you in a few minutes.